Okay, so our last two electrophilic aromatic substitution reactions that we're going to learn about have this special name, the Friedel-Crafts reactions. There's an alkylation and an acylation reaction, so we'll go through that. These are sort of special because you're creating new carbon-carbon bonds, which is always something that's a little bit, more powerful in our synthesis tool chest to do. They are reactions. So talking about the alkylation reaction, that means that I'm putting an alkyl group or just, a hydrocarbon group onto my benzene ring. My substrate's going to be an alkyl halide, so an alkyl bromide or an alkyl chloride, and then it's going to be catalyzed by, again, that aluminum trichloride or tribromide catalyst, okay? Just like before, what happens with that catalyst? You have the chlorine, it's going to come and make contact with that aluminum, right? The aluminum is a Lewis acid, it can accept this pair of electrons, and then that's going to cause this bond to break and form a carbocation. Okay, so this is our electrophilic species for these alkylation reactions, are just simply carbocations that are created. Everything that comes next should be pretty familiar in terms of it following that same sort of scheme that we've seen before. The ring or the pi bond in that ring is going to play the role of the nucleophile, attack that electrophilic carbocation. That creates this resonance stabilized carbocation, also known as the sigma complex. And then the last step here is similar to what we saw in our chlorination reaction that's catalyzed by aluminum trichloride. You have this complex here where this bond can reach out and grab that hydrogen, again, reforming your aluminum trichloride catalyst, allowing this pair of electrons to come down and reform that aromatic ring. Okay, and again, notice that I've created this new carbon-carbon bond. Creating carbon-carbon bonds is always something that's pretty powerful. Yeah. So this works best by far with secondary and tertiary alkyl halides because they form those more stable carbocations. If you're using a simple primary alkyl halide, and by simple, I mean specifically either methyl or ethyl, you can get away with it. Although we considered that we don't really think of primary carbocations or something that will form. So we think of this whole complex now as being the electrophilic species in these reactions, right? So basically it doesn't break off and form a carbocation. This only works though, if in terms of using primary alkyl halides, if you use those very simple ones. If you use anything more complicated, what can happen is you form your complex here, but this hydrogen is going to reach over and you're going to get a hydride shift that occurs in order to generate your more stable secondary carbocation, right? So that's the problem with using anything that's any bigger than in methyl or in ethyl. So for example, in this case, if you were to use one chlorobutane in these Friedel-Crafts reactions, you would actually only get like 35% of your butylbenzene, whereas 65% would be a result of that hydride shift that occurs. Okay, so you would get this rearrangement as your major product. Other limitations to the Friedel-Crafts alkylation reactions. So first of all, your halogens need to be attached to sp3 hybridized carbons, meaning that you can't use a vinyl chloride or an aryl chloride. Remember, these do not readily form stabilized carbocations. Vanillic cations and aryl carbocations are not very stable. So no such reactions will take place. Again, that carbon that leaving group is attached to needs to be sp3 hybridized. Notice that these ones are not. Second limitation, and I don't know that I would really categorize this as a limitation as much as something that we just need to be mindful of, is you will often have polyalkylation that results. That really just means that you need to take a little bit more care when you're doing these particular reactions if you really only want the monoalkylated product. But nonetheless, it's just something that we want to keep in mind. The reason is because after the first step, right? So in this case, I have this monoalkylated product. Turns out that this species is actually a little bit more reactive in these reactions than the benzene itself. So that's why you have this polyalkylation product that we have to keep in mind. And then the third limitation is that if you're using a deactivated benzene derivative, and we'll talk more next chapter about what constitutes deactivated versus activated. For now, let's just note that this nitro group, nitrobenzene, would be considered a deactivated benzene derivative. There's going to be no such reaction. So basically, you can't just do a Friedel craft on any old benzene derivatives. You have to have, or rather, you can't have any sort of a deactivating group on there. And again, we'll see what that means next chapter. For now, just keep in mind that nitrobenzene is considered to be deactivated and will not react in a Friedel craft reaction. Okay, so then the other one is an acylation. So what is an acylation? So we've talked about this a little bit before, but I think we haven't really talked too much about it, so it's easy to forget. An acyl group is when you have, right? An alkyl group is just some hydrocarbon chain. An acyl group means that you have a carbonyl group right next to you, right? Like at that bond, okay? So this would be considered an acyl group here, where what's being attached to the benzene is first a carbonyl carbon and then some long hydrocarbon chain, okay? These reactions you can do Friedel craft reactions using what are called acyl chlorides. That's what this reagent is. And then again, we have our aluminum trichloride catalyst. Sorry, blanked on that one. And you will have now an acylation of your ring. Again, one of the hard parts of these reactions are what is that active electrophilic species? Well, just like before, the chlorine is going to attack that Lewis acid, the aluminum. This is going to create this weird looking complex here, but then this can actually break and form, it's called an acylium ion, where we have, it's basically a carbocation, but the carbon is a carbonyl carbon. Just important to know why an acylium ion is the electrophilic species, or how it can even form, is because you have this resonant stabilization of that positive charge. This might look a little bit weird. We don't really think of oxygen as liking to have positive charge, but the better thing about this structure here is that every single one of those atoms actually has a full valence shell, whereas if it's a carbocation, carbon would only have 6 electrons in its valence shell. But just know, acylium ions are resonance stabilized. All right, so then just completing the reaction mechanism for these. Again, my nucleophile is that pi bond in the ring. It's going to attack that acylium ion. Notice that they use this particular resonance contributor for the acylium ion. I don't care which one you use. It's actually a little bit less work to use the one where the carbon's on the positive charge, or where the carbon bears the positive charge, whatever you want to do. And again, what that does is form our sigma complex. All right, and then in the last step, we again have this basic species that's going to come along and grab that hydrogen, reforming not only our aluminum trichloride acid our Lewis acid, not really a standard acid, but catalyst, and then we can reform our aromatic pi bond. What are the benefits? What are the nice things that you can do with a Friedel Craft acylation that you can't do with an alkylation is to actually create those primary substituted carbons. So let me show you what I mean. First, you would do the Friedel Craft acylation reaction, but then you can hit this up with a reducing agent, as zinc and mercury in the presence of acid and heat, and that will reduce that ketone into, into just, replace it with two hydrogens. And that's how we can create in a fairly good yields these, it's not really primary anymore, but what we couldn't do with a primary alkyl halide, right? If we had tried to form this using the Friedel Craft alkylation method, our dominant product would have some sort of a rearrangement or a hydride shift. So this is another way that we can sort of get around that by using an acylation followed by a reduction. I guess it's called a Clemson reduction, The other sort of benefit with the acylations versus the alkylations are you don't have the sort of like polyacylated product thing to worry about. This species right here is relatively unreacted, so you don't have multiple rounds of substitution that are occurring. So that's just kind of another benefit that you can use these acylation reactions for.